On October 29th, 3I/Atlas, only the third confirmed interstellar object to cross our solar system, hits its closest approach to the Sun at a blistering 68 kilometers per second. If anything about what happens on October 29th could change everything about 3I/Atlas rings true, this is the moment that could reveal whether it's just a rock or something far more deliberate. Most online panic is debunked by real tracking data. So far, there's no sudden engine burn, no direct course to Earth. But as scientists pore over GOES-19 imagery and prepare for this critical perihelion, one simple maneuver, if it happens, would bend history, hinting at intentions, intelligence, and a destination no one on Earth has reason to fear. So what's the smartest first move for a visitor from the stars? And why does this critical date matter more than anything you've heard so far? From October 18 to 24, as 3I/Atlas approached its critical solar rendezvous, teams across the globe turned to every available data stream in search of confirmation. The challenge: the comet's path brought it so close to the Sun's glare that even the world's largest telescopes were effectively blinded. In this narrow window, some pointed to satellite imagery, specifically claims of GOES-19 data, as a possible solution. But the reality behind these images is far more nuanced and demands careful scrutiny. GOES-19, a geostationary weather satellite, was never designed for deep space astronomy. Its primary instruments, the Advanced Baseline Imager and Solar Ultraviolet Imager, are engineered for tracking storms and solar flares, not faint interstellar objects. The sensor's plate scale and sensitivity fall short of what's needed to pick out a magnitude 12 comet from the blinding background of the Sun. Even so, the idea of using such data persists, driven by the sheer difficulty of observing anything so close to the solar disk. For a credible ephemeris overlay, matching predicted positions to raw frames, scientists rely on a meticulous process. Each image must be time-stamped with millisecond precision, a task GOES-19 can handle thanks to its GPS synchronization. Yet the real challenge lies in astrometric calibration. Unlike dedicated astronomical cameras, GOES-19's optics and field of view are optimized for Earth, not the star field beyond. To extract a moving comet's position, analysts must align each frame to a reference catalog, correct for platform motion, and account for optical distortion. This step is non-trivial, especially when the object in question is dozens of times fainter than the satellite's usual targets. The workflow continues with differential tracking, shifting and stacking frames to reveal any object drifting against the static background. If a detection is possible, its pixel coordinates are compared to the predicted ephemeris, with every measurement carrying an error bar that reflects uncertainties in plate scale, centroiding, and timing. Only when the observed and predicted positions agree within these uncertainties can scientists say with confidence that the object is behaving as expected. In the case of 3I/Atlas, no peer-reviewed record confirms a successful detection by GOES-19 during the October solar conjunction. Instead, the most reliable trajectory data comes from ground-based and planetary telescopes before the comet disappeared behind the Sun. When it re-emerges in December, the same rigorous overlay process, now with instruments designed for the task, will be used to check for any deviation from its predicted path. Until then, the scientific method demands caution. Every claimed sighting must be backed by reproducible analysis, not just a visual overlay. This is how the astronomical community guards against error and ensures that, when something truly extraordinary happens, the evidence will stand up to the closest scrutiny. Rumors about 3I/Atlas have spread online faster than the comet itself. Social media posts claim everything from secret engine burns to invisible course corrections, none of which hold up under scrutiny. According to a recent statement from the International Astronomical Union's Minor Planet Center, there is no confirmed evidence of anomalous activity or deviation from the predicted ephemeris for 3I/Atlas prior to perihelion. That hasn't stopped forums and clickbait videos from circulating doctored images, alleged reverse thruster signatures, and dramatic overlays that promise proof of alien intent. The reality is much less exciting and far more demanding. Detecting a magnitude 12 object like 3I/Atlas near the Sun's glare is a challenge even for professional astronomers. Most of the viral claims rely on artifacts, camera noise, cosmic rays, or simple projection errors, rather than real detections. For example, a widely shared GOES-19 coronagraph video actually used frames from a weather satellite not designed for deep space targets. The supposed bright spot matching the comet's position, a hot pixel, not a hyperbolic visitor. The process of confirming a real burn or trajectory change isn't as simple as drawing a line on a JPEG. Scientists require time-stamped, raw data, processed with astrometric calibration and error analysis. Each frame must be checked against a precise ephemeris, with uncertainties documented at every step. Even a faint deviation in position must be reconciled with measurement error, instrumental drift, and known non-gravitational forces like outgassing. As Dr. Ana Garcia from the European Southern Observatory put it, if you can't reproduce the result with independent data and a documented pipeline, it's not science, it's speculation. The overwhelming majority of claims, about 95% according to several survey teams, fall apart under this level of scrutiny. No peer-reviewed study, no official alert from the Minor Planet Center, and no NASA bulletin has confirmed any anomaly or sudden maneuver by 3I/Atlas as it approached perihelion. Until the comet reappears from behind the Sun and new, high-precision astrometry is available, all talk of engine burns or course changes remains in the realm of rumor. The only thing moving faster than the comet right now is misinformation. For those hoping to spot a real sign of intelligent control, the best advice is patience and a healthy skepticism of anything that can't be traced back to raw data and a published method. Imagine a spacecraft racing past the Sun at nearly 70 kilometers per second, more than 200 times the speed of sound. In that moment, every drop of fuel it burns packs an outsized punch. This is the essence of the Oberth effect, a principle that transforms the Sun's gravity well into a kind of cosmic slingshot for any object able to fire engines at just the right instant. To see why this works, consider a simple analogy. Think of a car speeding down a steep hill. If you floor the accelerator at the bottom, the engine's power stacks onto the car's already high speed, sending it flying even faster. In space, the same logic applies, but the numbers get extreme. Kinetic energy, the energy of motion, increases with the square of velocity. So when a spacecraft is moving fastest, each unit of fuel delivers much more energy than it would at a crawl. Near the Sun, the gravitational pull is fierce. Objects like 3I/Atlas accelerate as they dive inward, reaching peak velocity at perihelion. If an onboard engine fires at that moment, the effect is magnified. A burn of just 7 kilometers per second, tiny compared to the comet's overall speed, can twist its outbound path by tens of degrees, sending it toward a completely new destination. That same burn, performed far from the Sun, would barely nudge the trajectory. This isn't just theoretical. The Oberth maneuver is a well-established tool in mission design. For example, the Parker Solar Probe uses repeated close passes to the Sun to shed velocity and tighten its orbit, maximizing the effect of each engine burn or gravity assist. The math is straightforward but powerful. The energy gained from a burn equals the change in velocity multiplied by the object's current speed. At perihelion, with 3I/Atlas moving at 68 kilometers per second, even a modest push translates into a huge change in kinetic energy. For a natural comet, only outgassing jets, streams of vaporized ice, can provide thrust, and these are usually weak and poorly directed. But for a hypothetical craft, this is the moment to act. The Sun's gravity turns every kilogram of propellant into maximum outbound speed, making it the most efficient place in the solar system to change course. This efficiency is why astronomers pay such close attention to perihelion. If 3I/Atlas were under intelligent control, Any deliberate trajectory change would almost certainly happen here. The resulting path would be dramatically different from what gravity alone predicts, and the difference would show up in precise post-perihelion measurements. Detecting such a shift isn't simple. Astronomers must compare predicted and observed positions, factoring in every possible source of error. But the physics leaves a clear signature. A sudden, sharp bend in the outbound trajectory, far greater than what outgassing or solar tides could explain. The Oberth effect turns the sun into a lever, amplifying small efforts into major outcomes. For 3I/Atlas, the moment of perihelion is more than just a close pass. It's a test of the laws that govern both natural and artificial travelers. Whether the comet remains on its predicted path or veers off on a new journey, the underlying physics will guide every step, and the evidence will be written in the sky for anyone patient enough to watch. Detecting a real maneuver by 3I/Atlas isn't a matter of dramatic sky watching or viral video. It comes down to the cold math of astrometry, measuring, with arcsecond precision, exactly where the comet appears against the background stars, and comparing those positions to the path gravity alone would predict. Every proposed engine burn or course correction leaves a fingerprint in the sky. The comet's position will begin to diverge, frame by frame, from the trajectory calculated months before. For scientists, the challenge is to catch this divergence early and to prove that it's real, not just noise or a fluke of measurement. The key metric is called delta V, the change in velocity an object experiences measured in kilometers per second. At perihelion, even a modest delta V, say 1 kilometer per second, is enough to bend the outbound path of 3I/Atlas by tens of thousands of kilometers over a few months. But the sky is vast, and the uncertainty in any single measurement can be significant. That's why astronomers don't just look for a comet that's off track. They quantify the minimum separation between the predicted and observed positions, and they set strict thresholds for what counts as a real deviation. A 1 kilometer per second burn at perihelion would produce a skyplane separation of about 20 arcseconds by the time 3I/Atlas nears Jupiter in March 2026. To be sure of detecting such a shift, telescopes need to achieve positional accuracy better than 5 arcseconds, ideally much tighter. For larger burns, the divergence grows fast. A 3 kilometers per second maneuver would create a gap of more than an arc minute, and a 7 kilometers per second burn would pull the comet several arc minutes from its natural path. These are differences that even mid-sized observatories or spacecraft with decent optics can measure with confidence. The process is rigorous. Each observation is time-stamped to the second. Its field calibrated against a catalog like Gaia DR3, and every centroid is checked for systematic error. Measurements are repeated over days and weeks, building up a chain of data points that either hug the predicted ephemeris or begin to drift away. If the drift exceeds the measurement error, if the observed positions pull away from the predicted track by more than the uncertainty envelope, the case for a real maneuver strengthens. To make these judgments transparent, astronomers publish so-called sensitivity tables. These list, for each possible burn size, the minimum sky separation expected, the required measurement precision, and the cadence of observations needed to catch the divergence early. For 3I/Atlas, the consensus is clear. A 1 kilometer per second burn is detectable if you can measure positions to within 5 arcseconds every few days. For larger burns, the bar is even lower. This is the yardstick by which all claims of engine burns, of sudden course changes, will be measured when the comet reappears from behind the sun. The upshot is simple. If 3I/Atlas fires engines at perihelion, the evidence won't be a blurry streak or a viral overlay. It will be a cold, precise, and reproducible shift in the sky, tracked across dozens of independent measurements and confirmed by the world's best astrometric pipelines. Anything less is speculation. The coming months will turn rumor into data, and data into answers. Earth, for all its appeal in science fiction, is a poor candidate for any incoming interstellar visitor seeking a foothold. The planet's deep gravity well demands enormous energy for landing, launching, or even orbital maneuvers. No probe, alien or otherwise, would waste precious resources dropping straight into the thick of it, especially when easier targets abound. Add to this the reality of human society. Over 8 billion people, a patchwork of militaries, surveillance networks, and planetary defense protocols. Any sudden arrival would trigger a global response, not a quiet welcome. As Dr. Marcus Lee from the Planetary Defense Coordination Office put it, Earth is the last place you'd want to make a surprise entrance. Recent mission data confirms that 3I/Atlas already brushed past Mars earlier this month, passing within 28 million kilometers with no sign of deceleration or landing attempt. If the object were targeting planets for contact or colonization, Mars, uninhabited, resource-rich, and lightly defended, would have offered a far simpler first step. Instead, the trajectory remained unchanged, a silent flyby. This fact alone undercuts the idea that Earth is next on the list. From a strategic perspective, skipping Earth makes sense. Any advanced intelligence would recognize the risks of stirring up a planetary immune response. The logical move is to avoid the drama and set sights elsewhere, somewhere easier to access, less defended, and brimming with resources. That's why the focus shifts to the outer solar system, where the rules and the opportunities are very different. Jupiter stands out as the next major milestone for anyone tracking 3I/Atlas. If an intelligent maneuver occurred at perihelion, the object would be on course to sweep past Jupiter's orbit on March 16, 2020, closing to within 54 million kilometers, about a third of the distance from Earth to the Sun. For mission planners, this is the prime rendezvous, a window where the trajectory, natural or not, will be tested against every prediction. The logic of the Jupiter playbook is hard to ignore. Ganymede, the largest moon in the solar system, offers water ice, a magnetic field, and gravity barely a seventh of Earth's. These are not just planetary trivia, they're the ingredients for life support, rocket fuel, and the kind of base building that sidesteps the risks of a deep gravity well. Callisto, farther from Jupiter's radiation belts, presents another safe harbor. Both worlds are rich in resources and free from human interference. The idea of digging under kilometers of ice for protection isn't science fiction here. It's a practical engineering choice for any advanced traveler. The inbound trajectory of 3I/Atlas has drawn speculation about its origin. Barnard's star, just 6 light-years away, sits in the same general region of sky as the object's approach vector. The math is daunting. At speeds near 60 kilometers per second, the trip would have taken tens of thousands of years. While no one can prove a direct link, the coincidence keeps the question alive in the minds of the global observer network. For those watching, the probability that 3I/Atlas is anything but a natural comet remains vanishingly small, roughly 1 in 1,000, according to the most generous estimates. Still, the next checkpoint is clear. As the object reappears from solar glare in mid to late November, telescopes will be trained to catch any sign of a course change. The countdown is on, and the world's astronomers are ready to see what, if anything, breaks the pattern. On October 29th, 3I/Atlas will pass the Sun at nearly 68 kilometers per second, its closest approach and a moment scientists have marked for direct observation. GOES-19 satellite data from October 18th to 24 confirm that, so far, 3I/Atlas has followed its predicted path with no detected anomalies. Despite viral claims, there is no verified evidence of engine burns or course changes. If an artificial maneuver occurs at perihelion, post-event tracking in mid to late November will be critical. A natural trajectory keeps 3I/Atlas outbound, but a sudden, unexplained shift toward Jupiter would demand further investigation. The object's interstellar origin is certain, but its true nature, comet or probe, remains unresolved. Its projected path brings it within 54 million kilometers of Jupiter on March 16, 2026. For now, the facts are clear. We stand at a rare observational threshold, guided by data, not speculation. What happens next will be measured, not imagined.